This is the second hour of Physics 1A for February 24th, and we're going to get right into doing some actual applications of these vector things we've learned about. We're going to talk about what's known as the first condition of equilibrium. So, what does the word equilibrium mean? Equilibrium in physics refers to a state in which a system is either completely at rest or is moving with a constant velocity. Those are the two possibilities. So in order to get equilibrium, you have two possibilities. You either have a system at rest relative to its environment, or a system moving with a constant velocity. Now, the word velocity implies both speed and direction. So when I say constant velocity, that implies moving in a straight line with a constant speed. Okay? Those are the two ways in which a system can be in equilibrium. So what are systems that are in equilibrium? Pretty much everything. Most of the world, when you look around, is doing one of these two things, right? If you look around the room that you're watching this in, pretty much everything's at rest. My cup is sitting at rest on my table here. My remote for my Roku is sitting at rest. I have a comic book that's sitting at rest on my table. My phone, everything on my desk is sitting at rest right now. My keyboard's at rest. So most things are at rest. And it might seem like that's not interesting. Like, why would we look at things that are at rest? But if you scale it up a little bigger and think about other things that are at rest, you'll see why. So things like bridges. So I live in San Pedro. There's this gigantic suspension bridge called the Vincent Thomas Bridge. And in order to make sure that that bridge doesn't break apart, all of the internal forces have to be perfectly balanced to make sure that it doesn't break apart, to make sure that it stays at rest, right? Because a bridge isn't very good if it starts to move, right? If it starts to buckle and break apart, it's not a good bridge. Same thing is true if you're constructing a home or a building. You want to make sure that all of the supports in the walls can support the roof on your structure. You want to make sure that your doors don't just kind of fall off when you open them, things like that. So most of the world around us is at rest, and that's why we start with this. It's also one of the simpler things to understand. In addition to this, there's also systems that move at constant speed. So for example, another system that's in equilibrium would be if you're driving along the road, and let's say you're driving down the highway and it's a straight highway, then if you move with a constant speed, so you're cruising at 70 miles an hour, then your entire car is in equilibrium because you're moving at a constant speed. The moment you slow down or speed up, it's a different story. Something we'll talk about later, right? So any system that's at rest or moving with a constant velocity is in equilibrium. And Isaac Newton figured out that the first condition that describes systems in equilibrium is that if you sum up every single force that's acting on the objects, it should add up to zero. The net force, we call this the sum of all forces, or the net force. And if you add up all the force vectors, they should add to zero. Usually, we break this down into two different pieces. Because it's a vector equation, any vector equation can be split into parts like this. If I add up all the x components of forces in my problems, those should add to zero. And if I add up all the y components of forces in my problems, those should also add to zero. And with just this one equation, we can solve a lot of stuff. Does anyone have any questions? It's pretty straightforward. Any questions at all? Okay. This is also known as Newton's first law. Newton's first law says that, any system, it's not exactly Newton's first law, but it's related to it. Newton's first law states that Any system that is at rest will tend to stay at rest, and any system that's moving in a constant velocity in a straight line will tend to keep moving in a constant velocity in a straight line. It's also known as the law of inertia. Objects that are moving tend to keep moving. Objects that are at rest tend to stay at rest, basically. All right? So, let's use this. Does anyone have any questions at all? Does this look like something you learned in your last physics class? Okay.
Yeah, I'm very familiar.
All right, so let's apply this idea that the sum of all forces has to add to 0 to we have about 7 problems I'm going to try to do. I don't know if I can do 7 problems in an hour and a half. It's almost impossible unless I just skip a lot of steps, and that's probably not going to be very useful to you. So here's our first problem. Find the tension in chords A and B. How big do I need to make this so I can draw on it? That's probably big enough. So I have a 100-pound object that is tied to, I don't know, maybe there's like a ring here or something like that, and you've got ropes hanging off each side, and then you've got ropes up here and up here. And our goal is to find the tension in this chord A and this chord B. So the method by which we do this is by labeling and drawing all of our forces as best we can to scale. So let's go ahead and do that. So we've got, we're going to have, acting on this little chord right here, I'm going to say there's going to be 3 forces, basically. We're going to have a force that points along chord B that goes this way. There's also going to be a force that goes along chord A that goes basically up this way. Shift it up a little bit. I'm going to try to draw this to scale, but I will probably not succeed. And I'll talk about how I did that in a second. So that's that one, those two forces. Let's call this one tension B. It's a tension force. Whoops. Here, we'll just switch it. And we'll call this one tension A. I'll make this one red. In addition, there's also going to be a downward force pulling this way. And really, just to simplify things, I'm going to say that 100 pounds, which is this weight right here, we're going to call that W. And we're going to say that basically that force pretty much pulls directly down on this right here. And there we go. Technically, there is a cable that has tension, and that tension just turns out to be equal to the weight in this particular case. That's not always true. If the system was moving, that wouldn't be true, but it's not moving. I really didn't quite draw this to scale. I want to, so I'll try. So I need this vector on the bottom to be basically as tall as this plus that. So it needs to be at least that tall. And then we have to add a little bit. All right, so that's my attempt to make that vector. Okay, so next thing we do, we've labeled the forces. I'm going to write a little step-by-step process about how we're going to do this. First thing, we're going to draw what I've just drawn here, which is called a free body diagram. So FBD, free body diagram. It's basically just draw all the forces. Step 2, we're going to define our XY axis systems, XY axes. Okay? We can do this in any way that we want to. For this problem, I think the simplest thing to do would just be to draw the kind of normal ones, like this, and just put it, I'm going to try to stick this right in the center of my diagram right here, like that. So that's going to be my axes, and when you define axes, you also have to define what's positive. So we'll call this positive x over here, and I'll say this is the positive y direction right here. The next thing we do is we are going to break all of our forces into components. Components we learned about last time, and the way that they work is you basically do the following. This TB points at an angle, so I'm going to break it into a force that goes this way, and I'll break it into another component that goes this way. Because we know that if I have a vector that goes to the right and a vector that goes up, those two vectors add to the diagonal vector right there. And let's move this right here. to represent this thing here. And then what I'm going to do is label what these are. Now, I have to be really careful here because I know that people often really don't like subscripts. But let's see if this makes sense. If I call this one TBX and I call this one TBY, is that too many subscripts, or does that make sense what I mean by that? X component of TB and Y component of TB. Is that clear enough? Okay, good.
You're good.
We'll do the same thing on the other side, up here. And we got to break this one up. Sometimes this is easier than others. Sometimes it's hard, as we'll see in some of the other problems. So I get one that goes this way, and then one that goes up this way. And I'll shift them so that they look right. This one should be coming right up to the tip of that one. And then that one, hard to click on. It's good enough. I think that's good enough. So then we'll call the bottom one down here. I'll call that one TAX, and we'll call this one TAY. The weight vector that points downwards, that goes down this way, we don't need to include that one, right? Because it's already been broken up. It's already pointing in the y direction. Okay. Okay. Step 4. The next step is we need to use the first condition of equilibrium. All right. So let's do that. This is going to represent two different equations. One of the equations is going to be net force in the x direction is equal to 0, and the other equation is going to be net force in the y direction is equal to 0. Okay? That represents two equations. How many unknowns are we trying to solve in this problem? 2, right? And can you all tell me from what you remember from your algebra classes, how many equations do I need if there are 2 unknowns? At least 2. That's right. Always something to think about when you're doing these problems. Because if you have 3 unknowns and you only write down 2 equations, you can't solve it, right? It's not possible. So it's a good thing we have 2 equations, because we only have 2 unknowns. Okay, so let us do the x direction first. X direction is easy. So for the x direction, what we'll say is there's two forces in the x direction, right? TBX and TAX. W points down. Since the right direction is positive, we're going to write TBX minus TAX is equal to 0. Now, this says you're summing, but it doesn't mean add. Always. It can mean subtract. If the vector is pointing to the left, it's going to be negative. If it's pointing to the right, it's going to be positive. Okay, so next thing to do is to write down the other equation. The other equation is going to have TAY, TBY, and W, which will be negative. So we'll write TAY plus TBY minus W equals 0. And I can already see we're going to have some problems here, so we'll just take our rules and put them over here. And that'll allow us to shift this way and have a little more room to work with. There we go.
Mr. Murdoch?
Yeah.
Why is it that we subtract TBX minus TAX and the other one we add?
Because TBY points upwards and TAY points upwards. So positive vector, and then this will be the negative vector here. Whereas TBX was positive. See, I don't know how well this comes out on your screen, but can you see that there's an arrow right here at the end?
Oh yeah, I see. I got it now. Thank you.
Okay, you got it, no problem. Other questions? Okay. And now that we've done that, really all there is to do is to just solve the problem. Now, in order to do that, we need to use these angles that we have here. Okay. So maybe down here at the bottom, I'll write some things out here. So I would say that if I want to find what TBX is equal to, that all I would do is just write TB times the cosine of 45. Yes, it's negative W because it points down on the y-axis. That's right. And think about it. Weight is pulling. The weight pulls down, right? Physically. And the chords pull up, right? That's what this equation says. It says the upward force of the chords minus the weight equals 0. Because it's balanced, right? Okay. TBX, I would say, is going to be TB times the cosine of 45. And then TBY is going to be equal to TB sine 45, because it's opposite the angle. Like I was saying last time, you got to get really good at just seeing this stuff. I want to ask you guys to figure out for me, what will TAX be?
Cosine of TAA cosine of 30.
That's right. And then TB at TAY, or just T, is equal to TA sine 30. All right, let's put everything together. This is where I always say we're done with physics now. I think that's right, Chris. What you said is right about the 150 degrees. You can do that, so it'll become negative. Yeah, if you want to. Okay, so all the physics is done. That's it. This set of instructions, these 4 pieces of information here, this is how you do all these problems. And if you're lost and you don't know what to do, just do this. It will work, as long as you write down all the forces and stuff. Anyway, from here on out, it's just a bunch of math. Okay? I'm going to run through the math. You try to keep up if you can, but it's a bunch of math, so it's not going to be easy. Do your best to follow. So TBX is TB times cosine 45. I'm going to move this one to the right-hand side, so it just becomes equals TAX, which was TA cos 30. I cannot solve that equation quite yet, so we'll go to the one over here. This one says TAY, which was TA sine 30. Please watch carefully, as I may make a mistake here. Just try to catch it as soon as you can. TBY, get the sine 45. And then I'll move the weight to the right-hand side, equals W. We could go ahead and write that as 100 pounds, I guess. But then I gotta write 100 pounds every time. That's fine, though. What do we do next?
I want to say for the f of x side, you can divide for cosine 45 to the other side.
Yeah. That's right. So we can kind of isolate TB, right? Exactly what Googleplex said. That's
Exactly.
Right.
Yes, exactly.
So we'll get TA, and it's going to be multiplied by cos 30 over cos 45. If at this point you wanted to just calculate what this quantity is, because it's a number, you could. Oops, didn't mean to draw over like that. But then we basically just take this, and we're going to plug it in right there. So, what we get? Plugging in for TV this entire expression here. Next step, TA appears in both of these terms, which means we can factor it out. write this like this. It's cosine 30. I think sine 45 over cos 45 is tan 45, right? Just so we have less things to plug into our calculator. And then really, the simplest thing to do at this point is just calculate what this quantity is. So let's do that real quick. Sine 30 is a half plus cos 30 times tan 45. I think tan 45 is 1. So we get 1.366 right there. So we have 1.366 multiplied by the tension in chord A is equal to 100 pounds. And then we can just say TA is equal to 100 divided by 1.366 pounds. So whatever that is. Yeah, 73.2. I didn't round anything. I just used the entire value that was in my calculator. And of course, the units on this are going to be in pounds. And we're halfway done. We've solved for one of our variables. Usually the first one is the hardest because the second one is, we're just going to plug into that equation. Okay. Did everyone follow that? Does anyone have any questions?
On your calculator, it should be on radians, right?
No. You want to be in degrees. Because 30 and 45 are in degrees. In this class, you're going to be using pretty much degrees. Pretty much all the time. Up until the very last chapter. Simple harmonic motion. Yeah. So if you're coming from your math class, be sure to switch back. I'll try to remind you. Okay, so TA was 73.2 pounds. We plug in and we multiply by cos 30 over cos 45. We can do all that in one calculation. And we get, again, I'm not rounding at all, so if you get something a little bit different than what I get, try not rounding. And the reason why I'm doing that is because that is what you have to do for mastering physics. You wait until the very, very last step, and then you round. Okay, this one goes out to a 5, so we'll say it's 89.7, but you may get 89.6 depending on where you round off. And that is what I get. And it is not newtons. This is something I'm going to do frequently. A lot of these problems are going to have pounds in them, and I'm going to forget. I'm going to put newtons in there. And there we go. Any questions? That's pretty... The weird thing about this problem, it's about as basic as you can get without being just in one dimension. But you can see that there's still quite a bit of math. You know, it's not an easy problem. It's an easy problem, but it's not that easy, you know? Okay.
We'll be working with more than 2 dimensions throughout the semester?
Maybe once or twice, but usually not. Usually it's just... Like, later on, we're going to talk about objects that are not points, but instead are like balls and cylinders and stuff. So in that sense, there'll be 3 dimensions, but usually you can write the problem in 2 dimensions, so you don't need to worry too much about it. 3 dimensions really starts to show up in 1B and 1C. Yeah. Okay, if there's no further questions, I'm just going to keep going. Now, I really want to get through as many of these problems as I can, so I'm going to start off kind of slow, but I will pick up the pace as you start to, as soon as you all seem to start picking this stuff up quicker, I'm going to pick up the pace. Okay, let's bring this down with us so we can have that on the screen while we're solving this problem, so you can see that it really is the same process every single time. So here's the second problem. I don't like this problem actually. We're not going to do this one today, because I think it's a little bit too farcical. Like, it's not realistic. Most physics problems aren't realistic, but that one in particular, it has a massless object, and I don't like massless objects. Let's do this one. This one requires that we talk about friction. So we'll talk about friction, and then we'll do this problem. All right, friction force. Friction force is probably something that you learned about in a previous physics class. Now, how it was taught, I don't really know, so I'll teach this as we need to. So in general, what friction is it's a force that kind of tends to oppose motion. So this is how we kind of describe it. So if I have an object and it's on a table, let's say. Oh man, why am I drawing at such a weird angle? I apologize. Let me sit back in my chair so I can draw better. So if I have a flat surface, and on that surface I have an object, I'm really going at an angle a lot here. I don't know. Oh, is it doing an inked shape? That would explain it. Turn that off. So let's say I've got a block, okay? And let's say it's moving to the right with some speed. We say that if there's friction on this surface here, meaning that there's something that's kind of tending to slow it down, as most surfaces have friction, then there tends to be a force of friction that acts back this way. And the symbol we use for it is F sub k. So F sub k stands for what we call kinetic friction. And in order to define what it is, we need another force. So this object of mass m is going to have other forces acting on it as it slides across the table. It's going to have its weight that points down like this, but it's also going to have a force that points up like this that we call the normal force. We call this the normal force. And the word normal just means perpendicular. So it always points perpendicular to your surface. Right? And to find the value of what the friction force is, we use something that's called the coefficient of kinetic friction, and you multiply by the normal force. As you can see in the problem below, this quantity is a number that's commonly given in a problem. And it's usually between 0 and 1. Although I think for certain types of like tires, I don't want to say too much about this, but sometimes this can be greater than 1 in the case of specially made tires. I don't know about this one. I think this one always has to be between 0 and 1. Maybe I'm wrong. But yeah, mu k, we call it the coefficient of kinetic friction. It is a number that represents how rough the surface is. So for example, if you think about like a Teflon pan, Teflon's doesn't have much stick to it. You drop an ice cube in it, it's going to glide around really easily. That'd be kind of a low kinetic friction. If you take an ice lake and you take a piece of ice and you slide it on the lake, that's also going to be a really small amount of kinetic friction. Compare that to something that's going to be higher. You might have like your sneakers that have rubber on the bottom, possibly. When you walk on concrete, that's a really high amount of friction. So the coefficient of friction there may be pretty high. Between the wheels of your car and the road, your wheels are designed to grip the road really well, so it's another high coefficient of friction. That's pretty much it. Burning rubber, yeah. So that's kinetic friction. That's one type. And then the other type of friction is what we call static friction. So static friction is best probably seen by looking at like a sloped surface. So let's say that I have a block, and let's say that it's sitting at rest on the surface right here. Well, the only way that's possible is if there's some friction, because this object has a weight that goes down like this. It feels a normal force that points up this way. And what that means is that the weight would tend to propel the object down the ramp. So at the surface of the object right here, we would say there must be some type of force of friction that points back this way. And it can't be kinetic friction because the object's at rest, so we call it static friction. This one has a little bit different definition. The static friction is going to be less than or equal to what's called the coefficient of static friction multiplied by the normal force. Okay, so mu sub s is the coefficient of static friction. It's generally the case that between two surfaces, mu s is going to be bigger than mu k. It's easier for an object to slide along a surface than to kind of get it going, so to speak, when it's sitting at rest. The way I think about this is imagine you're trying to push a very large box that contains like a refrigerator or something like that, and you're trying to push it across maybe a cement floor. It's quite difficult to get the box moving to begin with, but once it starts moving, it's not as hard to keep it moving. Does that make sense? So pushing a very large box across a flat surface with a lot of weight inside, it's going to be harder to get it to start moving than it is to keep it moving. Does that seem in line with your experience? Were y'all following along with that? Okay. It's not entirely just because of friction. Part of it's because the object has some momentum, which it wants to keep moving, but it has some inertia. But anyway. Okay, so there we go. That's static friction and that's kinetic friction. Now, why is there a less than or equal to sign here? Well, the reason why is because the maximum value of static friction, here, let's write this as the maximum value, so we'll call it F max, and we'll put a little s down here. The maximum value you can have is mu s multiplied by n. Okay? But if the object isn't, how to put this? If external forces acting on the object don't actually reach this value, then the friction force is going to be smaller. So imagine the same system that we have right here, okay? But let me change one thing. Suppose that we make the slope steeper. Like this. Kind of almost comically steeper, because it'd be very difficult to imagine an object sitting on a surface like this and not moving. But let's say it's possible, just to kind of exaggerate this. The thing is that when the object is on a steeper ramp, the weight that tends to propel it down the ramp is going to be bigger. So if we say the weight is this way and the normal force is up this way, I would argue that your friction force now is going to have to be much bigger to keep it up, right? Even if it was the same surface. So this friction force would be bigger than that friction force because you need more friction force to prevent it from sliding down, right? To keep it still, if we say both of these are at rest. And so that's why, depending on what this angle is, the size of the friction force may be big or small. If you let the surface come all the way down to a flat surface like this, what happens to the friction force? If I have a flat surface, you got your normal force this way, you got your weight this way, perfectly balanced out. You don't even need friction for it to sit still, right? Would you all agree? No friction needed in this case, right? But if there's a slant, a slope, you need some friction to keep it moving. So that's how you can kind of see that you get the friction force is less than or equal to this quantity. There's a maximum value, but it doesn't mean you always have that maximum value. To drive this home even further, can I? Let me put this to where I can actually see the camera, and maybe make it just a little bit bigger so I can make this point. Nope, it's not letting me do that. Come on. Get here. There we go. So let's say that I have a flat surface like the surface of this right here, and I put on my surface. I don't know how well that shows up. Does that show up very well? Okay, we'll use my cup. You can see the cup, right? Right. So let's say that I have this completely perfectly level, right? There is no friction force if it's perfectly level, right? If I tilt it, maybe there's a friction force. How else could I get a friction force to show up other than tilting it? What do y'all think? How else could I get this thing to have some friction
moving it.
I don't want to move it. I want to leave it still. I want to have some friction force show up on my cup here. What would I do?
Change the material? I mean, that's
No,
not
no, no,
enough.
no, 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 no. Something that I can physically do right now. I'm not able to. I don't have powers of. I can't change colors of things. I can't change the material.
Blow on it.
Blow on it,
Blow
sure.
on it, blow air
So,
on it.
so if I were to blow on it in this direction, what direction would the friction force be? If I blew on it this way, or if I push it opposite, right? Yeah.
Towards you.
And if I blow on it or push on it in this direction, friction
Opposite
direction is
way, yeah.
back the opposite way, right? So there's kind of a break point, right? I can kind of tap this object, and if it doesn't move, there's friction, right? And we call it static friction. But if I push too hard, it starts moving. And now we're talking about kinetic friction, right? Now, depending on how hard you push, the friction force is going to push back exactly as hard until you make it move, right? That's kind
Can
of
friction be counted as energy?
no, it can't. We haven't talked about energy yet, but friction is just a force.
Okay.
Now, you could say something like, let's say you're in a car, you're driving along the road, and so you're driving along the road, driving really fast, right? And you see a stop sign in front of you, and you hit your brakes, so you slide to a stop, right? The friction force in that case has the effect of slowing your car down, which means it has the effect of kind of dissipating the energy from your car and kind of turning it into heat. So in that sense, friction may be associated with energy. Is that what you were thinking about? I don't know.
Yeah.
Okay, yeah. So the friction force could do work. And that work could kind of sap energy from a system. So you got a car that's moving, it's got kinetic energy, the friction works on it, it slows it down to zero, it turns all that kinetic energy into heat in a way that basically is a type of
Yeah,
kinetic
because like I see Priuses, like hybrid cars, like using like the like brake energy as a way to like charge electric motors or
Right,
something.
right. Now that's something really cool that people have been doing is that that in the braking process they try to recover some of that energy by storing it in batteries and stuff like that, right? Yeah, that's a really clever way
That's
to
cool.
make your system more efficient because those type of losses due to braking and stuff like that normally are very difficult to get back, so to speak. All right, so now that we've defined what friction is, we can maybe quickly do this problem. And we'll take another break. Okay, so where'd my stylus go? All right. So in this problem, it says if mu sub k is equal to 0.2, find the tension T required to move the block at a constant velocity. Remember that one of the conditions, or one of the types of equilibrium occurs when you have constant velocity. Okay, so let's look through our steps. The first thing we are supposed to do here is we're supposed to draw a free body diagram. Now normally, what we'll do is we'll draw it off the picture, because it's just normally how we do it. So let's start drawing some forces. So first of all, we've got a tension force that points kind of up at an angle like this. Label that one T. What other forces are acting on my block here? You can type in chat.
You have the friction force on the surface and it's pulling towards the left direction, which is the opposite.
There you go. Yep, there's going to be a friction force that points back this way. And I'll try to make it to scale. Should be roughly okay. So I'll call that one F sub k, and then the people write the other ones, normal force and the weight, exactly. So draw this in there. And that's the normal force, and then the weight will go the other way. So we got N for the normal force, W for the weight, and then we're also, okay, that's that free body diagram, done. Second step, define XY axes. There we go. There's our axes. I'm going to adjust the other vectors so that they actually look straight. Oh, they look pretty straight, actually, don't they? I think we're good. All right, so there's our axes. I guess I should probably make the axes like a little bit different color. Make it red. we're not doing that because then it's going to obscure the other things. We'll just do that. Okay, so those are our axes. Black. Why do you pick black? Black. There we go. That is the x direction. That is the y direction. Okay. This angle, 30 degrees. Next step, break forces into components along these directions. So there is only one force that we have to break into components, and that is the tension force. So we will do that. It's going to have a component that goes this way. I'll make that one red. And then it's going to have another component that points up, like this, from there to there. Remember that when you draw your components, if the vector goes up and right, then your component should go right and up. Right? Sometimes people will kind of draw something like this. Well, not like that, but sometimes people will draw stuff like this. And it may look the same to you, but it's not the same. Because this says go right and then go down, which would technically be a vector down here. Like that way. Okay? So make sure that if the vector goes up and to the right, that your components also go up and to the right. So there we go. Just like before, we will label these. On this picture, we might be able to label more than one thing. So this is t sub x. Can you all tell me, in terms of trig functions, what is this going to be equal to? It's going to be equal to the size of t, which we don't know, but it's just t. And we multiply by cos 30. That's exactly right. Hopefully you're getting good at just seeing that. 30 is adjacent, so you do t cos 30. Opposite, sine. So this will be ty, and it is equal to t sine 30. Which happens to be equal to t divided by 2, but we'll just write it as t sine 30. Okay, so we're done with free body diagram, define axes, break forces into components. The very last step is to use our force equations. So we got net force in the x direction is equal to 0, and we've got net force in the y direction is equal to 0. And again, let me just, now that we've done this, I don't know how much room we're going to need, but we'll move it over there. All right, let's do the x direction. In the x direction, we have exactly two forces. And I think I did a roughly okay job of making it so that this vector that points to the right is equal to the vector that points to the left from, like, the length, right? It's not exact, but it looks about the same. Why is that important? It may not be important to you, but I think it helps to visualize what's going on. Because the acceleration is 0, force is equal to m times 0. Yeah, that's one way you can think about it if you want to, Louis. Constant velocity, yeah. All right, so tx, t cosine 30, points to the right, so we'll make that one positive, minus f sub k. Okay, there's one equation. The y direction, we have three variables. We've got n, ty, and w. So we have n is positive, plus ty, or t sine 30. And then w is down, so minus w. And there we go. Anyone have any questions about those equations? Once you've gotten to this line, physics is done. So you do math. Right? Physics, math. It's pretty important to separate them from each other sometimes because I think often people try to do too many things at once. I don't know. Everyone's separate. Oh, this was equal to 0. My bad. Okay, I don't see any questions, so I'm assuming that everyone's kind of got this. I'll give you a couple more seconds, though. If you do have a question, please ask.
I have a small question.
Okay. Good.
I was gonna say, kinetic friction and then the other static friction. Can you explain it like a little bit more so you know differentiate?
Let's come back to that later so we can actually finish up this problem. Because we're going to go on a break here in a second. I'll come back and I'll explain that. All right, let's go ahead and solve this. How many variables do I have here now? How many unknowns do I have?
2.
2? What are they? List them.
Just t.
Well, that's 1. What else is there?
And normal force.
Normal force, that's another one. What else? Is that
You
it?
know the weight though.
We don't know the weight. Oh, we do know the weight. Sorry.
We do know the way.
What's the? There's another thing we don't know actually. What is it? Friction. Yep. Okay, can I solve this problem with just these two equations?
Yeah, I believe so.
I can tell you. I guarantee you can't because there's three unknowns, right? How many equations do we need if there's three unknowns?
At least 3.
3. Okay. So what's the other equation going to be?
Friction equals coefficient times normal.
The normal force.
There you go. That's right. So that's our third equation right there. So let's put that in to this equation here. So this equation says t cos 30 is equal to fk. So I'll just plug in uk times n. All right, there we go. Now we're down to just two unknowns, which are basically, we got rid of this unknown, so we're just these two, t and n. And our goal is to find tension, so we actually don't even care about t in this particular problem. We're still doing ink to shape, apparently. So all we want to do then is just eliminate the normal force. Okay. So to do that, I guess we could use maybe this equation. And then plug all of that in for n.
Professor, quick question.
Mm-hmm.
How come the normal force wouldn't cancel out because of the weight since it's not moving?
Because of the tension force pointing up this way, the normal force is actually going to be slightly less than the weight. Think about like when you lift up on an object, it kind of like reduces the normal force in a way.
I got you. So let's say if it's a sticky surface and you try to lift something off that sticky surface, it's a little bit more than just the weight itself.
The normal force gets lower when you try to lift it up like that. Yeah. Mm-hmm. Yeah. A little bit less than the weight. In this case, what's going to happen is that this normal force plus the tension in the y direction is going to be equal to the weight, basically. All right, let's keep going. So this equation has one unknown now. It's just t. We factor out the t. And then what weight was 20. And we'll just calculate this quantity here, which I guess I need to plug one other thing in. So it's cos 30, and then uk was given in the problem as 0.2, right here. And then we'll just calculate that quantity right there. We'll get t times cosine 30 divided by 0.2 plus sine 30 equals 4.83. And it has no units, right? Because the cosine is just a fraction, the sine is just a fraction or a ratio, and 0.2. The coefficients of friction, they don't have units. Okay, it's 20. And so then t is going to be 20 divided by 4.83. And of course it's pounds, so about 4, right? A little bit more. And again, I'm going to keep I got 4.14. This problem really only has one significant figure, right, in all these numbers, but I'll just write 4.1. I think that's fine. Are we in pounds? Yeah, there we go. I'm just going to say in general that I don't assign very many problems in this class, and I don't do many problems in this class, Googleplex, where the normal force is equal to the weight. I just don't. You know? Does that make sense? None of you should ever assume the normal force is equal to the weight, because I can almost guarantee you it will not be in like 90% of the problems we do, okay? The normal force is almost always going to be an unknown that you solve for, all right? Almost always.
The only reason why
This is not physics 2A. This is not your high school physics class.
That's why.
The normal force is never going to be equal to the weight in this class. Everyone understand? What were you saying? Sorry, I interrupted you.
No, you explain it because it was basically just my last physics 2A. They just said normal force is the way we just cancel that out.
Mm-hmm. Yeah, I'll respond to that when I'm not recording. All right, so this is our tension, and I think that's the answers. We're done. All right, we're gonna take a break until 10 minutes, so 4:20. So break till 4:20, and we'll come back and we'll try to do some harder problems, hopefully. And I'll try to answer your question about friction, the person had asked as well. Okay, come over here and we'll stop.